Segment 1. Size scales. In astronomy, the distances that we deal with are very large compared to the distances we deal with on a normal day. So we need to have different yardsticks by which to measure these distances, yardsticks that bring the unfamiliar into the realm of the familiar. Let's start by looking at the yardsticks that we use on Earth. A human being has a size between 1 and 2 meters typically, and this size scale is typical of many of the objects that we deal with in everyday life. As we move beyond what's immediately around us and start to look at our larger surroundings, the size scales get considerably larger. Here's a satellite image of the Austin metropolitan area, with the dark area on the left being Lake Travis and the dark area on the right being Decker Lake. In between is the city of Austin, and the double-headed arrow shows you a distance of 10 kilometers, which is about the distance across town, about 6 miles. As we move to the full size of the Earth, about 1,000 times larger, the Earth is 13,000 kilometers across, about 13 million meters. The circumference of the Earth is about 40,000 kilometers. Moving still farther back, with this image that was taken from a satellite orbiting Mars, we see that the Earth-Moon distance is about 400,000 kilometers, about 30 times the diameter of the Earth. In this cartoon, we're seeing the relative sizes of the planets by putting them up in front of an image of the Sun, and the Earth-Moon distance is again shown here. The Sun is about 1.4 million kilometers across, and that's about 3 times the Earth-Moon distance. In this picture, an actual photograph, the little dot that you see to the left of the dash is a sunspot. That sunspot is about the size of the Earth. It would take about 100 Earths stacked end to end to equal the diameter of the Sun. So in astronomy, there are 3 commonly used distance scales: the meter, the astronomical unit, and the parsec. The light year is a popular distance unit, which we will not talk about much, but I want to bring up since many of you are familiar with the concept. So the meter we have established on the surface of the Earth as a standard distance. The astronomical unit, which is about 3 times 10 to the 11th meters, about 300 billion meters, is the distance from the Earth to the Sun. A light year, which is about 10 to the 16 meters, is a unit of distance. So it's just like an astronomical unit, only bigger. And a light year is the distance that light would travel in 1 year. The parsec, which is an astronomer's unit that's used very commonly in astronomy, it's about 3.26 light years. It's about 3 times 10 to the 16 meters. It's also about 200,000 times larger than the astronomical unit. Let's take a look at what some of these yardsticks stack up against in real astronomical objects. Starting with the astronomical unit. By definition, it's the distance from the Earth to the Sun. So it's the size of the Earth's orbit, which of course is larger than the orbits of Mercury and Venus that are also shown here. In this next size, we see typically the sizes of the different orbits in the solar system. In this case, the Earth's orbit is very far tucked in towards the center. The Sun is shown a little bit unrealistically large in this illustration. Jupiter has an orbit of about 5 astronomical units, about 5 times the distance from the Earth to the Sun. Neptune's orbit is about 30 astronomical units, and Pluto's orbit, that now discredited planet, has a somewhat elliptical orbit with a typical distance of about 40 astronomical units. So the size scale of the solar system is on the order of 40 or 50 astronomical units if you don't count some of the minor bodies that are a bit farther out. And so it's about 80 astronomical units across. This illustration shows you the area immediately around the Sun, where the nearest stars are around the Sun, and the individual circles here, each one is 1 parsec, about 200,000 astronomical units. So the solar system, remember, is about 40 across, and the distance to the nearest stars is on the order of 200,000 astronomical units, 1 parsec. So this shows you out to 5 parsecs or so, our nearest neighbor stars. And what you realize is that the solar system is tucked up in very close to the Sun, and there's a lot of space before you get to the nearest stars, which are hundreds of thousands of times farther away. Going to an even larger scale, here's a picture of the Whirlpool Galaxy, which is a typically sized spiral galaxy. and it's about 20,000 parsecs across. So the nearest neighbor stars are a few parsecs away, and this distance is about 20,000 parsecs. So about 10,000 times larger in size. And our own Milky Way galaxy is very comparable in size to this, on the order of tens of thousands of parsecs. So the individual galaxies are arranged in space along with other galaxies. And the next slide shows you what's known as the local group, that is, the galaxies that are close to our own Milky Way galaxy. In addition to the Milky Way, it contains one very large galaxy, the Andromeda Galaxy M31, and the number of so-called dwarf galaxies. In this illustration, down at the bottom, I've put in a double-ended arrow that's about 1,000,000 parsecs across. So while the large galaxies in this picture are 10,000 parsecs across, it takes about 100 of them to cover the distance from one to the other. Going to an even larger scale, what's called the local supercluster, we see the nearby galaxies in the local group together with other galaxies that are in the same region of the sky and actually close together. And on this scale, instead of the 10,000 parsecs we saw before, we have 10 million parsecs. It's about 10 million parsecs from the local group to the Virgo cluster. So this is our neighborhood, as it were, in the whole universe. On the largest scales, here's just an illustration, a kind of cartoon of the evolution of the universe since the Big Bang, something we'll talk about later. It makes less sense to talk about distances because look-back times, the time since when the light left you, starts to become important. But the universe is about 13 billion years old, so a typical scale for that size is about 5 billion parsecs. And that's about the largest size scale that we have to deal with in the universe.